Hey everyone, it's Justin again. Today, you get to learn about what the circumcenter of a triangle is, and more specifically, what perpendicular bisectors have to do with the circumcenter. You'll probably find it very helpful to use about 4 different colored pencils or fine point markers in this lesson. Before you get started, go collect some now so that you have them ready. By the end of this lesson, you will be able to apply the properties of the circumcenter to compare lengths and solve for unknowns in a triangle. First, we'll explore how to find the circumcenter through an activity in your notes template. Then, we'll complete one multi-part example problem. This is the first page of your notes template for this lesson and has a link to follow that will provide you with a visual representation of the circumcenter. This visual is interactive and allows you to move the vertices of the triangle to see how the circumcenter changes. There's a graphic organizer with blanks for you to fill in after you explore the visual representation. It may take you some time to really grasp what's happening in the visual as you move the vertices of the triangle. Giving it the time it deserves and analyzing everything that's happening in the visual will make things easier later on. So pause this video, follow the link, and work on the page. Take as much time as you need to be confident about what circumcenter means. Let's check your work with the key before completing an example problem. Go ahead and check your answers now. If you had something wrong, it's really important that you go back to the link for the visual again and explore that idea that you were missing. Pause the video so you can do this now. Let's move this to the side so we can refer to it while we go into a little more detail here. The first part about the perpendicular bisector is pretty familiar since we learned about this earlier in the course. We draw a segment that meets at the middle of the side and is perpendicular to the side. We can do that for each side of the triangle. For this side of the triangle, here is the perpendicular bisector. For the next side, here's the perpendicular bisector. And for the final side, here's the perpendicular bisector. Where all 3 of those meet is the location of the circumcenter. That brings us to this part of the key. The circumcenter is the same distance from all 3 vertices. So if I draw in segments going from the circumcenter to each vertex, I can mark all of those as congruent. The circumcenter is also the center of a circle that goes through all the vertices of the triangle. When we take this away, it makes it easier to see that these 3 segments are also the radius of the circle, giving us another reason that they're congruent. Anyways, here's the circumcenter. Hopefully you're comfortable with finding the circumcenter and you're ready for our multi-part example problem. If you need a moment to rewatch any of this or get prepared, now's a good time to pause the video. This example problem says, given that point A is the circumcenter of triangle BCD, complete each statement below with an inequality, equal sign, or numerical value. Did you notice that I used a shortcut for writing triangle here? It looks like a little equilateral triangle, and we can use that symbol for any triangle, even when it's not equilateral. Also, these pictures may seem a little overwhelming, so it's always good to lay some groundwork before answering the questions. Your different colored writing utensils will come in handy here too. You just learned that the circumcenter is the point where the perpendicular bisectors of the sides meet. This means EA, GA, and FA are the perpendicular bisectors of each of their sides. We see this perpendicular symbol but we don't see any markings telling us that the sides of the triangle were bisected. This means that BE is congruent to EC. What else can we mark as congruent? BD was bisected by point G, making BG and GD congruent segments too. The same is true for CF and FD. All right, we've taken care of any congruences that exist due to the perpendicular bisector part, but what about the circumcenter part? What does circumcenter mean? Can you add some segments to this picture that would be congruent because of the circumcenter at point A? We can think of the circumcenter as the center of this circle that goes through all the vertices of the triangle. We can draw in these 3 lines, which represent something special in the circle. Do you know what they represent? What if we take away all these other things for a moment? What do these 3 lines all represent? They're each the radius of the circle, making them all congruent. Okay, let's bring back all our other markings, and we can get rid of the circle so it isn't in our way. Now we're more prepared to fill in the blanks for this problem. Remember to use an inequality or equal sign when doing comparisons like in these problems. And find a numerical value in problems with an equal sign, like these problems. And just a heads up, the Pythagorean theorem is a good trick to have in your tool bag, because we do have a lot of right triangles here in our picture. Go ahead and give these 5 parts a try. If you get stuck, especially on the last 2 parts, it's totally okay. I'm going to go through them with you after you've had a chance to try. All right, let's go through these to check your work and clarify anything that you may be wondering about. The first blank wants us to compare the lengths of AC and BA. We already figured out when we put these markings here that they're congruent, so this makes their lengths equal to each other. Our next comparison is between segments AC and CF. Remember, this right triangle I showed you earlier? Well, since it's a right triangle, we know that the hypotenuse will be the longest side, making AC longer than CF. Okay, now let's check out EC and EB. We actually marked those as congruent earlier, since that side of the triangle was bisected at point E. Therefore, we can say their lengths are equal. Now we have 2 more parts to answer. If you were unsure of these when you looked at them earlier, let me give you a hint. Think right triangles and the Pythagorean theorem. We're wanting actual numbers to represent lengths for these answers here. Pause the video and see if the Pythagorean theorem can help you out on these final 2 parts. All right, we have to find what AC equals. The fact that this is a right triangle is going to come in handy again, because that means we can use the Pythagorean theorem to find the missing hypotenuse length. Substituting in 3 and 4 and solving for the hypotenuse gives us 5 for the length of segment AC. Finally, we have segment GD that we need to find a length for. Did you think of this right triangle and the Pythagorean theorem again? Did you use 5 as the length of the hypotenuse, since earlier we found that AC is 5 units, and we also marked that AC and AD are congruent? Finish this problem now if you haven't already. Substituting 5 into the Pythagorean theorem as the hypotenuse and 2 as one of the legs gives us the square root of 21 as the missing leg, and the length of GD. We have officially answered all parts of the question. Awesome work! If you want to go back and watch any parts of this video again, now's a great time to do so. Now you can apply the properties of a triangle's circumcenter to compare and find lengths and You can remember to use the Pythagorean theorem if you need to when there's a right triangle involved. We're going to learn about some other special segments and triangles in the following lessons, so don't forget that it's the perpendicular bisectors that form the circumcenter. See you next time!
Hey!